you guys can talk to. So
Okay.
let's see, what do we got? So we start off up here. This is when we jump right out of the airplane, right? This is time 0. And it's at this point that we have a certain drag of k. 1/2 times the density times 1.95, which is the drag coefficient of the body of the skydiver, times their area, the cross-sectional area of the skydiver.
Oh, and I think all the k should be multiplied, or just multiplied by like v squared to get the actual forces, but
Of the, oh, to get the
Yeah.
actual drag force?
yeah, but
Yeah, because this is just the,
but it's the same in all of them.
this is another drag coefficient, right?
Mhm. Yeah.
This will be times v squared to get the complete
Yep.
drag force. Yeah. And then we go to time 0, which is when the ripcord is pulled. This is when the suspension lines are starting to be released, so the canopy is yet to open. It's just the lines that will be pulling the skydiver upward, and it gets a brand new k of 1/2 times the density times, this is the same set of drag as up here because the body of the skydiver hasn't changed at all, but we add in drag based off of the suspension lines.
And this term starts with when t is equal to t1, it starts off at 0, and the term in the parentheses goes to 1 when it gets to,
Yeah.
or when it's at t0, it's 0. When it's at t1, it's 1. As far as,
Yes.
yeah,
I
okay.
believe that's right.
Yeah, that makes sense.
Yes.
Okay.
Yeah. And it's also at this point that we get a brand new level jerk, right?
Mhm.
Jerk is continuous here, then it changes, and now we have a new level of jerk. Because jerk is a continuously
Mhm.
piecewise function compared to everything else is straight continuous.
From t0 to t1, or at t1, I think it jumps up from, or is at t0 it jumps up from 0 to,
Not necessarily 0, but it makes a jump.
okay. Hmm.
And then at T1 is when the canopy opens. It is released from the backpack.
Then we'll
And
see a
begins
much
to
bigger jerk
Hmm?
there.
Yes, this is when we're going to get our major jump and jerk. Jump and jerk. I don't like that. And this is also when the body changes its positioning, whether the skydiver wants it to or not. It flips upright.
Hmm.
And we get another new K value of 1/2 times density times 0.35 times a new area.
So that area is just, before it was the bottom of a circle, I think, or
Before
It's-
they
yeah,
were
it was-
spread
it was-
eagled,
before it was, yeah. Oh,
Yeah.
before they were spread eagled, and now.
their feet first.
Yeah.
or
Okay, yeah.
first.
Because their positioning has changed, so their cross-sectional area has changed. So the amount of points that are hitting wind and drag force is changing. And then here is the drag of the parachute, and that has turned into a time function because the parachute is constantly being deployed during this time. And we have
Let's see.
graphed A of t over here. This is at T1. It is just kind of starting to constantly increase between T1 and T2.
Mhm.
And then it reaches T2. That's the point where it's fully inflated. This is the steady state that it will be eventually leveling out and having a constant area at.
But at this point, it goes past it because the reason it gives in the paper is that there's the momentum of the air is still there.
Yes, momentum is there. It's making changes in how the parachute is reacting, and it needs to find a steady momentum, right?
Mhm.
Conservation of momentum. Canopy is fully inflated. We get a new K value during this time. It's still reliant on that A function here. It's just we're focusing in on a different subinterval of A, right? Just this little hump of it's gone past the steady state area, but it hasn't leveled out yet. And then drag of the skydiver is still the same as before because his position hasn't changed.
So the skydiver doesn't change after this.
He is in a constant, we're assuming he's in a constant
Oh, yeah.
position, right?
Mhm.
Yeah.
And
That's another variable.
okay.
And then at time 3, we return back to the steady state. So we have passed the hump of change in momentum, and we are back at the where A is going to be falling for the rest of the trip.
Yeah.
Right?
Yeah, so A1 is just, yeah, that's the final area.
Yes. So we reach A1 right here. I should write that down. This is A1.
And the paper doesn't give an actual equation for A. It just says that it starts at a certain value and ends at a certain value and is
The
continuous.
paper proves that it is both continuous and differentiable.
In that interval? Or?
Yeah.
Okay, yeah.
In this interval specifically. And that is the only interval that we care about.
Okay.
So, whatever happens on the endpoints and beyond, we don't care about. This is what we're focusing on.
Okay.
And then once we've reached that A1 again, that steady state area after T3, we have a brand new K value. Once again, we're assuming the same positioning of the skydiver, and we have a constant area now for the drag of the equipment, and so we have the same K value as we're falling. It's still dependent on the height, and that's
Yeah.
because of altitude, right?
Height, I think height's just the, height's just a constant. It's just the
Are you sure?
height of the guy, yeah.
Okay.
So it's just like 1 point something
So-
meters.
Yeah,
Wait, what is
yeah,
height of the guy at when?
height of the guy after he's like changed positions. It should just model his area.
It's H
Right here?
Yeah.
Yeah, because he flips up right, and that's when H comes in. So I would assume that's what it's.
Okay. Gotcha.
Okay, so he starts flat and then flips up, right?
Mm-hmm.
Okay. Let's see. Just thinking about
Am I
that a
missing
second.
anything else?
Don't think so.
Yeah, I don't think so. I think
You're saying
everything.
there's something
That
about the
is-
landing. You saying?
Great.
Or-
We want to look into more about the safe landing velocity.
Yeah.
I think that depends on how.
Mhm. I think the easy
It'll-
part
it'll
is
depend
that.
on when we pull the ripcord, actually, right?
And like surface area of the chute and that kind of
Yeah.
thing.
Are you talking about like if you open it closer to the ground, or?
Yeah. So if you open it sooner, you're going to reach a
Mhm.
safer velocity faster, right?
If you open too late, you might still be going fast,
Yeah.
even with your chute fully deployed.
Mhm.
Yeah.
Or
And well, I'm just. I think. Yeah, you have a certain velocity over time. It's just that the ground comes at a certain time. I get. Well, that's a bad way of saying it.
yeah,
But the good news is that at T3, everything's constant, so we can just plug the numbers in and solve for that.
Mm-hmm.
And that'll be the final. It'll like slowly go towards that terminal velocity. I think at that point it's one of the equations. There's some equation that we've done in class we can like solve for after that.
Okay.
Actually, all of these we can solve for, but anyway, that one
So
too.
that's the general summary of this paper, right?
Well, yeah,
yeah.
sounds
Cool.
good. Great.